Alright, I'm going to do example 15.6 for you. What we have is a big block sitting on the ground, which is labeled mass B, right here, and pulled all the way level with the ceiling is a big sack of flour or a sack of sand or something we're going to call mass A. And we're going to measure theta from that angle. So right now, it is we're going to call theta equal to 0. It is going to swing down to some theta final equal to 90 degrees. In other words, all the way down, right? Makes that easy. So they want to know what is the velocity of A and the velocity of B after the impact, and find the loss of energy after the collision. So we'll deal with the loss of energy after we figure out the velocities, because we will need those. Just a quick reminder too, this one is using feet, slugs, and pounds. So when they give us the weight of object A as 6 pounds, they're literally giving us the weight, just like something in newtons. To get its mass, we need to take that 6 pounds and divide by 32.2 feet per second squared, and we will get units of slugs. And the same goes for mass B. So I'm going to substitute those two things in anywhere I would normally put mass. Okay, so I want to know first how fast this bag is going to be going right before it hits. So I'm going to conserve energy. Alright, so let's do a T1 plus V1 is equal to T2 plus V2. In its initial state, it was held at rest, so it has no kinetic energy. It's going to turn into all kinetic energy. And we're told that this length of string is 3 feet, so that drop is also equal to 3 feet. We don't have any trigonometry to do here. We just have an mgh turning into 1/2 mv squared. Cancel, cancel. The velocity is going to be equal to the square root of 2gh. Alright, and that comes out to a 13.9 feet per second to the left, so let's call it a negative 13.9 feet per second. You'll notice your book does not use negative. I'm working it with our normal convention, right being positive and up being positive. Okay, so we have the velocity of A right before it hits and makes impact. So before impact. And that's negative 13.9 feet per second. Let's hold on to that. Now they're gonna hit each other. We were not told that they stuck together. Instead, in this problem, they're told that we have a coefficient of restitution, E equal to 0.5. So we are not going to move off together as one body. They're going to move off with their own momentum. So mass A will have its own momentum and mass B will have its own momentum. So let's conserve momentum. I'm going to get MAVA initial plus MBBB initial is equal to MAVA final plus MBBB final. Alright, for the mass, like I said before, don't put in the 6 pounds. It's actually 6 pounds divided by 32.2. So we have that number. We know the velocity right before the impact is negative 13.9. Make sure to get your signs correct here. and mass B was not moving, so we're going to get that 0. Mass A is 18 pounds divided by 32.2, but we don't know its velocity, so let's just call it VA final. I'm sorry, this should be a 6. And same thing for the 18-pound mass, divide by 13, or 18-pound object, divide by 32.2 to get the mass, and that will be the velocity of B final. Okay, if we cancel all these little things and then divide everything by 6, we can simplify this down to VA final is equal to 13.9 minus 3 VB final. Alright, let's hold on to that equation. Notice we have 2 unknowns. This means we're going to have to use the coefficient of restitution E. So let's do that. They say, I'm going to go ahead and write the whole formula. E is equal to the velocity of B final minus the velocity of A final divided by the velocity of A initial minus the velocity of B initial. The big block on the ground is not moving, so we can cross it out. We know what the speed of A was before the impact, so we can actually put a value in there. And I get 0.5 is equal to the velocity of B final minus the velocity of A final, all divided by that negative 13.9. And we can rearrange this and also solve it. I don't know how I do that. For VA final is then equal to VB final plus 6.95 if you move that to the other side. Call that equation number 2. If we set 1 equal to 2, we get the following. The velocity of A final is equal to a positive, it's either a 1 or a 2, I can't read my writing, 1.74 feet per second, and the velocity of B final is equal to a negative 5.21 feet per second. So the book is going to solve it by assuming the directions go to the left, and that is positive. Okay, the next part is how much energy was lost in this collision. Well, we can just look at how fast the object, either object, was going before and after the collision. I'm going to look at mass A. If we remember, we can define work as the change in kinetic energy, or T2 minus T1. That work, if we look at oh, I hear the president speaking right now, sorry. If we look at the work done from 1 to 2 for the system, I'm going to say this is my T2, this is my T1, and I'm going to fill in accordingly so I don't make any sign errors. The kinetic energy, if we remember, is 1/2 mv squared, so I'm going to have a 1/2 MAVA final squared plus a 1/2 MBVB final squared, and then our initial terms. Well, B was not moving, so it gets 0, and we have a 1/2 MAVA initial squared. Okay, we have all the numbers, we have the velocities, we have the masses, we can figure out the work done for the whole system from 1 to 2, and we get 10.1 feet pounds. and they're going to give that a negative sign because that energy is lost. No system in this case should gain energy. We had a coefficient of restitution that literally means that deformation took place and energy was lost. So you should see some change in kinetic energy for your object or for your system if coefficients of restitution are involved. Thank you.